So last time let's look at the big picture for a while. So we started by we looked at the machine learning problem. We defined our problem, and then we said that there are two important resources. One of them is sample complexity, and the other one is computational complexity. Of learning. And the first part of the course, we focused on the sample complexity, and we showed that the sample complexity is completely controlled by the VC dimension, or if we are going to the more relaxed non-uniform learnability, we can control the sample complexity by having those weights or description lengths or some kind of a tool that incorporates a collection, an infinite collection of finite VC classes. So the sample complexity was kind of completely well understood. Then we looked at the computational complexity. So computational complexity was the question of how much computation time you need to invest once you already have the sample. And what we said, we first defined what's computational complexity, and then we claimed without proof that some very natural problems, ERM problems on very natural classes, are NP-hard, or in some sense, they are infeasible computationally. So now the question here is how can we overcome the computational hardness of learning certain classes. And the first answer that we gave is basically the first positive answer that we gave. So answer one was the boosting approach. So what was the boosting approach? You find some class which, although not as expressive as what you are shooting for, say we want to learn half spaces in some high dimension, we choose a class which is much more limited, which is just decision stamps. But the advantage of this small class, so we choose some limited class, basic class. We want to learn some H, we choose some limited class. The advantage is that for this limited class, we know how to do ERM efficiently. Now, how will this limited class help us? If we have an algorithm that, if the class is such that for our data, I can, no matter how I weigh the sample, I can always get an a gamma weak learner. So if I'm lucky enough, and with respect to this, just picking classifiers from the limited class, I can always get arrow which is bounded away from half. Then combining them together will give me a good classifier for H. Right? It doesn't violate the hardness of sometimes of learning H, because it's based on some kind of a luckiness assumption. We assume that our data is such that any manipulation we make in terms of weights to the sample, we can still find a gamma weak learner within the class B. And finding good learner within class B is efficient. So if we are in this good situation, then we can get a good learner for H. So that was one approach, the boosting approach. And the boosting approach requires iterations. And the smaller gamma, the closer our prediction to half, the less improvement we make with iteration. But we're still paying in terms of sample complexity for each iteration multiplicatively. So that's what we analyzed last time. Now today I want to look at a different approach, a different answer. Which in some sense will say we want to restrict our attention. We want to ask what kind of learning problems can we solve with some known efficient algorithms. So we want to somehow restrict our attention. Maybe we can focus on classes that we know how to solve how to learn efficiently. So now we try to kind of characterize a big family of efficient learnable tasks. And with this, we will also have some kind of generic algorithms that for those families, a fixed algorithm will work for every member of the family. So that's a different approach to answer the computational hardness. OK, and now for this second approach, the family that we're going to look at is basically involves a mathematical notion that I want to talk about today, which is the notion of convexity. So what we are going to do today is talk about this mathematical notion of convexity, and maybe only towards the end of the lecture we will go back and connect it to learning. And convexity, we mentioned it before, but not. I want to pay more attention to it. So let us start this notion, which is completely mathematical, and we start with the notion of convexity of sets. So we say, so our first definition is that a set, say, X subset of Rn is convex if for every xy in X and alpha between 0 and 1, the vector alpha x plus 1 minus alpha y is also in X. So that's a mathematical definition. We can immediately explain it with a picture. So what does it mean? I have some set here. This is my set X. Now I pick 2 points, X and Y. And now I can play with alpha. What will I get if alpha equals 0? If alpha equals 0, which point do I get here? 0x plus 1 times y, which point do I get? Y. I get the point y. If alpha equals 1, which point do I get? I get 1x plus 0y, I get the point x. And when alpha varies between 0 and 1, I get all the points on the line connecting, on the interval, linear interval connecting x and y. So what this definition says is that if x and y are in my set, so should be every point on the linear interval connecting them. So is this set that I drew here, is it convex? No. Why not? Because I can find here 2 points, say this is my x, this is my y, and I draw the line that connects them, and I have some point on this line that goes out. So this set is not convex. Okay? And convex sets have some nice properties. So we already mentioned it in the context of proving, if you remember, the VC dimension of half spaces. We use the fact that every half space, every linear half space is convex. So examples of convex sets are, of course, balls in Rn, but also linear half spaces. Right? A linear half space is the set of all points x in RD such that, so that is the linear half space defined by W and B, such that the dot product X W plus B is greater or equal than 0 or less or equal than 0 in both cases. So let's call it W plus LB and linear half space and L minus WB. And we will repeat the same definition with less or equal 0. In both cases, it will be convex, because if I take my space and I cut it with a line, and I look at everything below it or everything above it, in both cases, if I take 2 points here and connect them, all of the interval is going to be on the same side as these 2 points. So half spaces are convex, and balls are convex, and we have all kinds of nice properties of convex sets. So we have nice properties, some nice properties of convex sets. For example, if A and B are convex, then so is A intersection B. Because if I take a point to X and Y which are intersection, then X and Y are both in A, and therefore this intermediate point will be in A, and X and Y are both in B, so the intermediate point will also be in B, so the intermediate point will be in both A and B. And the corollary from that is that we can also define the convex hull as we did before. And so a corollary from this is that for every set A subset of Rn, there exists a set convex hull of A which is convex, and for any convex B superset of A, this convex hull of A is a subset of B. So it's the minimal convex set containing A. Yes? Okay, so I have here some set A. Now I take this set, the convex hull of A. So if I have any convex B that contains A, I want the convex hull of A to be inside B. So I can take the intersection of all the convex B, B prime, whatever. I take the intersection of all the convex sets that contain A. Since intersections are convex, the result is going to be a convex set. And this convex set is going to be a subset of every convex B that contains A. So the convex hull of A is just the intersection of the set of all B's such that B is convex and A is a subset of B. I take the intersection of all the sets which are convex and contain A. By this lemma, it's a convex set, and since each of them contains A, the intersection will contain A. And I'll get this property that it is minimal among all the convex sets containing A. Yes, what was the question?
Isn't this statement trivial because the empty set is convex?
What?
Isn't the statement
But the empty set doesn't contain A. Oh, which is convex. Okay, that's a very good point. I'm embarrassed Embarrassed that I missed. So what did I miss here? Which is convex. A is a subset of the convex hull of A. That's very important, yes. It's the minimum set which is convex and contains A. What? Yeah, it's kind of a bonus. For all those that are worried whether you should drop off the course today or not, if you are not doing well enough on the assignments, you still have 1 month of classes. Oh, not how much? How much do we have? 2 weeks. 2 weeks of classes. So 2 weeks, so you can collect 20 points or something in 2 weeks. Okay, so this is the minimal convex set that contains A, of course. Yes?
It's very minor, but don't you need to show that infinite intersections?
Yeah, it's infinite intersections, right. I need to show that infinite intersections, but the same argument holds for infinite intersections. It's a good point, but that was knowingly I avoided this complication. Yeah. Yes?
So does that suggest that the convex set A has a larger size than A?
The convex hull of A may be larger than A. If A is not convex, you see, if A is not convex, if A looks like this, this is my A. It's not convex. So what will be the convex hull of A? It will be, I'll have to complete it, to add things to make it convex. Okay? So this is convex sets. But what we want, so that's one component that we will need, the notion of a convex set. The next component that we need is a notion of a convex function. So the next component that I need is a notion of a convex function. So we have here a different definition. And I say that a function f, f that goes from Rd to R is convex. So now we need to define a convex function if for all x, y, and alpha between 0 and 1, f of alpha x plus 1 minus alpha y is less or equal alpha f of x plus 1 minus alpha f of y. So this looks, on first sight, it looks like it's a different definition. We will soon see that the two definitions kind of relate to each other. So what does it mean in terms of a picture? What is a convex function? So consider, for example, a function in R2, and a function that goes from R to R. So say that my function looks like this. This is the graph of my function f. So what does the convexity mean? Assume that I have here a point x, and here I have a point y. What is the point alpha of x plus 1 minus alpha y? It's some point here. Alpha x plus 1 minus alpha y. Right? What is f of alpha x plus 1 minus alpha y? F of this is this point. Right? I look at the point alpha x plus 1 minus alpha y and see where it hits the graph. What is, so this is this side. F of alpha x plus 1 minus alpha y. What is alpha f of x plus 1 minus alpha f of y? So I look at f of y. This is f of y. I look at f of x. This is f of x. I connect them and look at the point alpha times this guy plus R1 minus alpha times this guy. So it means that when I connect 2 points on the graph of f, the line interval hangs above the graph of f. Does it make sense? Yes?
Yeah. What if you just flip this parabola the other way? 'Cause wouldn't the point f of alpha x plus 1 minus alpha y still be sitting on the hill on the function, and then we draw this chord connecting f of x and f of y, and then it's below?
Right. So this function is convex, but this function is not convex.
Okay. Yeah, I guess it's not necessarily that it holds for symmetry.
Right. The only, and we will see, so one could say, okay, why should I define this in convex and not this one? This I should call it concave, right? But the reason we call this one, we could have chosen each of them as the convex. The reason we chose this behavior to be convex is because of the following relationship to convex sets. So there is a connection between these two functions, these two definitions, definition of convex sets and definitions of convex functions. So we have a claim that connects the two, that f is, so my f goes from Rd to R, is a convex function if and only if now I'm looking at a set. The set of all x, y, such that y is above f of x is a convex set. Convex set where? Where does this convex live? Where does this set live? In which space does it live? X is a vector in Rd, y is a number, so this is in Rd plus 1. Okay. So if we go back to this picture that we had before, if this is my function f, this is called sometimes the epigraph of f. I'm looking at the set of all x, y, such that y is above f of x. So what I will get is I will get this set. This is the epigraph of f. Because here I have x, y. This is the point x, f of x. Y is above f of x. So this explains why I chose the word convex for these functions. Because if I look at this function and its epigraph, this function, if I look at all the pairs of points which are above the graph, it will not be convex. Because when I'll try to connect these 2 points, it will go outside the set. So the convexity for function is just induced by the convexity of sets. And this is just a very straightforward checking from the definition. Okay. So why do we care about convex functions and convex sets? So let us look at some properties of convex functions. So let us look at some properties of convex functions. And the first and maybe the most useful property for our purposes of convex functions is that convex functions do not have local minimum. So what is a local minimum? Assume that I have a function. I mean, intuitively, what's a local minimum? I have a function and I'm trying to find its minimum. So if the function looks like this, so this is going to be a local minimum. And this is a real minimum of the function. This is a local minimum of the function. And what is the problem with local minimum of the function is that if we are trying to find the minimum and we are trying to make progress, a greedy algorithm that always goes from a point to a point that has the value, a lower value of f, because I'm searching for the minimum. If I do a greedy algorithm and I start in a bad point, I may end up in a local minimum, which is not a minimum. Because I will not get out of here, because I want to find the minimum. I will not want to go in this direction, because then it increases the value of f. And I will not want to go in this direction. It also increases the value of f. So I get stuck here if I'm trying to use a greedy algorithm. If I have a local minimum. If I don't have a local minimum, if any local minimum is a global minimum, then greedy algorithms are not getting stuck. And this is going to be important because we are trying to minimize functions. What functions were we trying to minimize when we were doing learning? The loss. The ERM algorithm is trying to minimize the empirical loss. The algorithm for a structural risk minimization was trying to find the argmin of some other functions. So in many learning tasks, we're trying to minimize some kind of function. And the problem is that when the functions have local minimum, we may get stuck. So that's why we are so interested in convex functions. But now let me try to make this property precise. So I have to define what is the local minimum, and then I want to show you that convex functions do not suffer from this issue. Okay? So we have a definition here. Given a function f goes from some Rd to R, a vector, a point, U is a local minimum of f if there exists some r greater than 0 such that for all v in the ball of radius r, in the ball around u of radius r, or in other words, all v such that the distance between u and v is at most r, for all such v, f of u is less or equal f of v. Then I say that u is a local minimum, because I have, if we look at this example again, if I look at this point u, I can take a ball around it such that for every v in this ball, f of u is smaller than f of v. Locally, it looks like a minimum. Yes?
Don't you have to also say that there exists some other point not in the ball around u that is less than u?
Sometimes local minimum are also global minimum.
Okay.
So now I have my claim that if f is convex, then any local minimum of f is also a global true minimum. So if f is convex, then this will not happen. And you can see very clearly, this function is not convex. Why is this function not convex? Because if I try to connect these 2 points and I look at the line, it goes under the function. But we need to give it a formal proof, this intuition. So what is the proof? So let f be convex and u a local minimum of f, and pick any and let v be any other point in Rd. So now the local minimum, so we know that for some r greater than 0, u is a minimum among points in the ball around u of radius r. So now, here is my picture. I have here the point u. I have here the point v. And I have a ball around u where I know that here, I mean, my function now, I don't draw my function because now I'm two-dimensional. The function is here. I know that among all members of this ball, u is a minimum. But v may be outside this ball. So now I'm going to do a trick. I'm going to take the line that connects these 2 functions and pick a point which is inside the ball. So what we do is we pick some alpha greater than 0 such that alpha times u minus v is less than r. So I want to push it towards the inside the ball. So now I want to calculate the function. I want to use the convexity. So I know that by the local convexity, f of u is less or equal Now I'm getting, I want to make sure that I'm not getting confused between u and v. Okay, so I want to pick alpha. What I want to pick an alpha, so probably the other alpha promises it. So I want to pick alpha such that u plus alpha v minus u is in the ball of radius r around u. Okay, so now I know that f of u is less than f of u plus alpha v minus u. Because this point is in the ball, and f of u is the minimum in the ball. Yes?
You said pick any points in RD.
Right.
Don't you mean picking points on the function that you're...
No, the function is defined over RD. So it's a bit confusing because now, until now, I was drawing functions over R. Now it's a function over R2. Okay? So now I'm using so by the local convexity, this point is inside the ball. If I pick alpha small enough, this point will be inside the ball. And if this point is inside the ball, fu is below this f of this point. Now I'm saying this is less than f of u plus alpha. Or let me just rewrite it. So this is f of u plus alpha v minus alpha u. Right? So I can rewrite it as f of 1 minus alpha u plus alpha v. What is missing?
Are those two the same alphas?
I think so, but I don't care. I mean, pick an alpha like this. That's a definition that will help me. I think that this one will suffice to guarantee it. But just a matter of otherwise, you always can pick alpha small enough such that if you take u and add a small enough vector, you will still be in the ball.
So you're just going to scrap that definition?
I think that the alpha there will suffice for this, but otherwise, just don't bother with it. This is the alpha that I care about. OK, so far I just did very simple. This is the same as this. Now I'm using the convexity. So what do I know now? That this is at most 1 minus alpha times f of u plus alpha times f of v. This is by the convexity of f. OK, so now I can open the parentheses. What do I get here? I get here f of u. This is equal. F of u minus alpha f of u plus alpha f of v. OK, again. This point, I picked alpha small enough such that this point is in the ball. If this point is in the ball, then its f is above f of u. Now I just rearrange the terms here, and I notice that my point is actually 1 minus alpha u plus alpha v. Now I use the convexity to open it, and I just open 1 minus alpha f of u to write it like this. But what did we get now? Now I can take the f of u from here and from here, and they cancel. So this implies that my alpha f of u is less or equal alpha f of v, which in turn implies that f of u is less or equal f of v. So I showed you that if u is a local minimum, the value of f there is less than any f of v, no matter where v is, not necessarily in the ball. And we use the convexity to take this far v and argue about the local convexity to show that I'm still beating the v which is outside. So that's the most important property of convex functions, that they have this property of they avoid local minimum. Every local minimum is a global minimum. Yes?
Is there anything implying that alpha is positive?
That's what we chose alpha. We pick alpha, where was it? Pick alpha greater than 0 such that we need to pick positive alpha, right? And we can do it because the radius of the ball was positive. Right? So you see, if I have here is your point U. And here is the ball within which I'm ball of radius r, in which I'm minimum, right? And here is some point V. So what do? I look at the line that connects them. And along this line, I pick someone here which is already inside the ball. So how does this guy look? This guy looks like you can think of this guy as some u plus this vector. And this vector is alpha time u minus v for small enough alpha. Okay?
So this definition
So this point is the point u plus alpha times v minus u.
So in the definition of alpha, we need to count up.
Yeah, I had it there. I didn't copy it. Alpha is alpha greater than 0. Yeah. I mean, that alpha there will suffice for it. Okay? So are we happy with the proof? Is it clear what the local minimum means? And every global minimum is a local minimum. OK, so that's the main property. Now that we know that those functions are interesting, we want to show that actually they are living all around us. So we want to show which functions are convex. So the next thing I want to discuss is somehow give you an indication that there are many convex functions. So the first thing is just note that maybe it's very simple for. So first example, just consider functions that go from R to R, and assume that both f, the derivative and the second derivative of f exist. The functions exist. Then the following are equivalent. One is f is convex. 2, what does it tell me about the derivative of f, if f is convex? What? The derivative f of the what? F prime of x is a non-decreasing function. And 3, f2 prime of x is non-negative on every x. Right? So the slope, if I look at such a function and look at the slope is only getting higher and higher as I move with x from the negative side to the positive side. And if the slope is only moving higher and higher, then the second derivative, which is the rate of change of the slope, is always non-negative. So we can already conclude things that we already know. So corollary the functions f of x, c for every constant c, f of x equals x, f of x equals x squared are all convex. Of course, we could also see it from the picture, but the next thing I want to show you is some closure properties of convex functions. So some closure properties of convex functions. So the first one, which is nice, is that if f and g are both convex, then so is max, the maximum fg, which is defined as maximum f of g at every point x, is the maximum of f of x, g of x. And why is that? And again, we have to just check it. So proof, we just have to check the maximum. What does the maximum function of fg does on a point that looks like alpha x plus 1 minus alpha y? Right? And should we prove it, or you want to do it yourself? Let me leave it as an exercise. I mean, the kind of thing that is easier to try to figure yourself than to do it together. Yes?
Can't you also use the property of the convex set above it? You just take the intersection of the two.
So that's a good point. What is the maximum?
I think it's just
Very nice. So we have a very elegant proof here. Very, very nice. OK, so this is the, that's not the proof in the book, but it's a very elegant proof. So so this is the Christina, that's the name, right? The Christina proof is use the property of the epigraphs. So the epigraph of the function max fg, what is it? So you see the epigraph, here I have one function f. And here I have another function g. The epigraph of f is this. The epigraph of g is everything above g. So what is the epigraph of the max? The max function is g up to this point and f from this point on. So the epigraph of this is just the epigraph of f intersection the epigraph of g. A point is above the maximum if it is both above f and above g. And we have shown that intersection of convex sets is convex. So the epigraph of the max function is convex. And therefore, the function is convex. Because the function is convex as a function if and only if its epigraph is convex as a set. So this is a convex set. So the function max fg is a convex function. Yeah, very nice. Next edition of the book, we will have this one. Okay, now why do I care about this maximum? Because it already gives me something. So here is another corollary. And my corollary now is that the function absolute value is a convex function. Why is absolute value a convex function? How can I write absolute value as a maximum of two convex functions? Yes? Max of? What is f? Right. I mean, since, and the proof is, since x is just the maximum between two functions, x and minus x. And both functions are convex. And both f of x equals x and f of x equals minus x are convex. We can see it by the epigraphs, because the epigraph of f of x equals x is this set. The epigraph of f of x equals minus x is this set. And the intersection of both of them is exactly the epigraph of the convex hull of x. Of the, not convex hull, the absolute value of x. So absolute value is a convex function. Right? We need to increase our collection of convex functions. So I will add two more examples of convex functions. So we continue with closure properties of convex functions, and I claim that if, so this is another claim in the same spirit, that if f1 up to fn are all convex, and w1 up to wn are all greater or equal 0, then the function g of x equals sum I goes from 1 to n wi fi of x is also convex. Okay, and here the proof is very easy, straightforward, because everything is linear. So the proof is that we want to pick what is g of alpha u plus 1 minus alpha v, or alpha. Did I define it with x and y or u and v? Say x and y, they are most distinguishable. right? And if I look at this function, then I can write it as a sigma on I wi fi of alpha x plus 1 minus alpha y, right? And this is less or equal sigma wi alpha fi of x plus 1 minus alpha fi of y, because for each function we have this convexity. So for every function, the fi that I have here is below this combination of fi of x and fi of y. So here I just used due to convexity of the fi's. Now I can just rearrange the sum. So this is equal the sum of wi alpha fi of x plus the sum of wi 1 minus alpha fi of y. And then I can take the alpha and the 1 minus alpha outside the sum, because they are constant. So it's alpha sigma wi fi of x plus 1 minus alpha sigma wi fi of y. And this is just alpha g of x plus 1 minus alpha g of y. And it's one of those proofs that maybe it's easier to do on your own than to follow the derivation on the board. Now, the last type of functions that I want to show you that are convex, and they are going to be very useful for us, is convex applied to linear functions. So now what I'm claiming is that so another claim, for every convex G going from RD to R, the function f of x equals g of sorry, this is going from R to R, g and f of x okay, sorry. My new function is going to be, the new function is going to be f of w equals g of, now I take the dot product of w x plus y, and here x for any x in RD and y in R. So where f is going from where to where? So f is a function that goes from Rd to R. Is also convex. Okay, so what do I get here? I fix parameters x in Rd and y in R, and I take the dot product and add y. And again, the proof is pretty straightforward, and it just relies on the fact that, I mean, I have to insert here u plus alpha v. So the proof just evaluate f at the point w equals alpha u plus 1 minus alpha v for any u v in Rd, and use the linearity of the dot product wx. That is, we know that for any two vectors, I need to right, alpha u plus 1 minus alpha v dot product with x equals alpha u dot product with x plus 1 minus alpha v dot product with x. So that's the linearity and the convexity of G. So if I take the u dot product of alpha u plus 1 minus alpha v, the dot product with x, it's like taking alpha times the dot product with u plus 1 minus alpha, the dot product with v. That's the linearity of dot product. And if we use this fact, then we can evaluate f at this point, which is g of this. And it's going to be equal g of this, and this is less of g of the sum. I'm just letting it, the calculation, I leave it to you, but there's nothing here. Kind of just turn of the mill. Okay, so why do I care about this we will see in a minute why do I care about this function. This function is interesting because if we are doing regression, then this is kind of the loss that we are looking at. If I have a points here x, y, and I have here a line which is determined by a vector w, my loss in regression is so the regression corollary. So let's talk a little bit about regression. I don't remember if I talked about regression, linear regression. Did I talk about it at all or not? So linear regression is the problem. It's a very common problem in statistics. You get a collection of points, and you somehow believe that they are describing a phenomena that can be described by a linear function. So you're trying to find a linear function that fits these points as well as possible. So now we have to define a loss between such a function and the loss between such a function and the input. The input is the collection of points. So the loss that is common with linear regression, so we're given a collection of pairs x, y in Rd times R. So x is something that I measure, and y is some phenomena. Say x is parameters that I measure. Say I want to know how big is going to be a baby. So in x, I measure the height of the mother and the height of the father and the weight of the mother before the pregnancy and the weight of the mother at 8 months. And here is my value for the weight of the baby. So I can do these measurements for many babies. And I'm trying to predict the weight of a new baby by a linear function. So I'm trying to find a linear function of this that best predicts y. So the loss, a common loss for linear prediction, for linear regression, which is a search for the best linear function that predicts y from x, is the squared loss, which is the loss if I have here a w that describes the weights of a linear function, and I have here a point x, y. A common loss is to look at w x minus y and square it. So this is called the square loss. So for every point, I look at the square loss, and I'm trying to find the linear predictor that minimizes the sum of squares. And my claim is now, the corollary from this, corollary from what we did so far, is that for any x, y, the square loss is a convex function of w. W is what I'm searching for. I'm searching for the best line. I have data which are these points, and the loss is a function of w, and it's a convex function of w. And that will be useful for learning such functions. So I want to switch now in my last 5 minutes to how does this connect to learning, and of course we will talk about it more in the next lecture. So I want to switch to connect it to learning. So we want to talk about convex. So here a definition. What are convex learning problems? So let me remind you the general setting of learning that we talked about. Our general setting of learning, the general learning task was defined by a triple x, h, z, and l, where h is some set of model or hypothesis class or set of models that we want to choose from. Z is my space of instances. These are the points that I see, the points that I'm trying to predict. In the case of the 0, 1 prediction, Z was x cross 0, 1. And L is some loss function. Loss function. So the loss function takes a model H from H and takes some Z and gives me some positive number, which is my loss. So this is something we discussed before, but maybe it was quite a long time ago. So let me just remind you. So in particular, we focused on the binary prediction with 0, 1 loss case, in which Z was some x cross 0, 1, and L of some hypothesis H, when it's given a point in Z, that's a point in Z, was 0 if H of x equals y, and 1 if H of x is not equal y. So that was this is a general setting, and we mostly focused on the case that Z is points with labels, and you check how well H predicts the label. But in general, it could be more general. I mean, H could be any model, Z could be something more abstract, and we just need to know a loss. How well does the model behave or fit the particular instance that we have at this moment? And now we want to define what is a convex. So I just have time for the definition. I'll have to get back to it next time. So what I define is what is a convex learning problem. A learning problem is convex if the domain if H is a convex subset of some RD, and for all Z in Z, the loss L of Z is a convex function. So this function goes from RD to R, because it takes here an element of H, which is a vector in RD, and outputs a loss, which is an element of R to R. So these are convex learning tasks in which my space of hypotheses is a convex set and the loss is convex. Now, so far we talked about H's, which were functions that predict. Suddenly, my H's here is a subset of RD. But I can think of it as linear predictors, where the W is just the vector of coefficients of this linear predictor. OK, so that's as far as we can do today. Have a nice weekend. Your assignment 2 are returned here, so you should come and pick it up.